Hello everyone, I'm the Leviathan from the Libresilicon project, and in this video I will explain to you how to actually make use of the Libresilicon manufacturing process standard and how to scale it from a small laboratory configuration up to industrial mass scale manufacturing levels. The main difference between an industrial scale manufacturing machine and a laboratory setup is that an industrial scale machine has the capability of loading batches of silicon wafers at once, which are provided to said machine in cassettes as depicted here in the slides on the left. While in a normal laboratory setup, you usually only load one wafer at a time using a pair of tweezers. The reason for the bulkiness of most of the industrial level machines is exactly the required mechanics to perform all this batch loading and unloading into empty receiving wafer cassettes. The biggest problem, if you have ever tried to manufacture some semiconductor prototypes with a foundry, is that there is a minimum quantity you have to buy before they even start talking to you. In addition to that, they make you go through a load of NDAs in order to even give you basic information on how to start designing your circuit with the highly proprietary and secret manufacturing process. In addition, for getting a foundry to even talk to you, and not a really big problem, is that as soon as you have designed a chip and tested, you've burned through hundreds of thousands of US dollars to have a feasible, working, sellable product. And which can only be manufactured with that specific foundry. As soon as this foundry goes out of commission, may it be natural causes, earthquakes, or bankruptcy, you are screwed. You have to go through the entire prototyping, development, R&D again to adapt your design to another foundry, which costs you yet another 100,000 US dollars or more. This is also a really significant reason why I decided to start Libresilicon, in order to introduce a semiconductor manufacturing process standard, which allows portability, to a certain degree at least, between multiple foundries and laboratories. My goal is not to convince large already established manufacturers to adapt the Libresilicon process standard, but to take the power out of the hands of those very same and put all those secret manufacturing recipes into a public open source domain, allowing small startups to form and fairly compete in a free and open market, because that's how a free market capitalism is supposed to work. Large corporate entities with government funding, under government control, they do not care about transparency issues in semiconductors, because they are perfectly fine, because the government profits from the possibility to put spy backdoors into chips, into the products of their pet companies they're running. Those big companies, funded by government, by taxpayer money, money extorted from people, that's the lucrative merger between state and enterprises. Or as this one funny Italian guy coined it, corporatism, of which he was super proud, because it was an important part of his new societal order he just had come up with, the word for a bundle of sticks in Italian. By the way, the idea behind this project is to unseize the means of production, which are right now in a majority in the hands of the government. I want to make it impossible in the future for anyone to use intellectual property laws to wage warfare against other countries and their economy, like it happened in 2019 when the US administration back then forced Synopsys to cancel the licenses they had granted to Huawei. This is an unacceptable situation that most of the broadband IP cores, which are needed to build a halfway modern smartphone or any other telecommunication device, are in the hand of a few government-controlled entities. This has to stop. In short, Libresilicon aims to give you everything you need to get started, to get your own little startup off the ground, at least from the know-how perspective. May it be chemical recipes or ideas how to design the process flow, how the safety manuals on chemicals, how to use certain machines. It's a collection, a knowledge database, if you want, on how to make a working CMOS chip or even a flash chip, because in my design I also have CMOS flash, silicon oxide, nitride oxide silicon. This all collected in one place where you can find answers to your questions. How do I build this? And since I'm an ANCAP, I figured I'll also make a print version of it at some point. It's fitting, the Anarchist's Semiconductor Cookbook. And yeah, it started as a joke, but I guess it's really something worth thinking about. I mean, having a print book. Here a picture of a buddy of mine, Victor Lee, and me working together in the clean room at Hong Kong University of Science and Technology. I assume you already know how transistors work since you're watching a talk about how to manufacture transistors. This slide is only for refreshing your memories. Let's say we have here a transistor with a gate, source, drain. Only difference between an NMOS and FET is that in a NFET configuration, the bulk, or also known the body of the transistor, is tied to the source, which shorts one of the two integrated diodes which are naturally occurring due to the p-n junction in a transistor. And so you get the free integrated freewheeling diode in an NFET. So if you put the voltage here between the gate and the source, what happens is that you basically have an electric field charging the capacitor, pushing electrons into the p-doped material, and due to recombination, you start opening a channel. First, the recombination leads just to the change from p-doped to neutral silicon, and the higher the voltage becomes, the further you overcome the required bandgap energy to turn the p-doped silicon into virtual n-doped silicon, and that creates here a channel between the two n-doped zones, which is also virtually temporarily n-doped. That's why NMOS and NFET are also known as n-channel transistors. This is only temporary, of course, unless you put too much voltage into, then the black magic smoke comes out of the part, and it's permanently conducting, which in the business we engineers call also broken. This is an n-channel. Also here, n-channel, same thing. The more voltage, the higher the conductivity between n plus through source and drain. As you can see here in an NMOS, from an engineering perspective, source and drain are interchangeable. And FAT, however, because one of the two junctions is being tied to the bulk, there you actually have to take care about the polarity of the transistor. In practice, source and drain, also in NMOS manufacturing, can vary depending on what purpose this NMOS has been made for. So you should really follow the pin assignments in the datasheet when designing your circuitry. Values from the datasheet, like the drain source resistance, the capacities between those drain source gate pins, they are influenced by not only the gate oxide thickness or the bonding wire resistance or the width of the channel, but also by manufacturing specific factors in the actual transistor and its interconnects on the die, into which I will go in the following slides. While building standalone transistors can be achieved with relatively simple equipment, as soon as you want to start to integrate transistors into something more useful, like into logic gates or even further into processors, you need to start isolating logic gates from each other in order to prevent latch-up effects. It doesn't matter whether you perform a very large silicon integration or VLSI for short, which works down to 500 nanometers or 350 nanometers, which can still be isolated using low-cos, or whether you are doing ULSI, ultra-large silicon integration, which is needed for very, very small feature sizes, like 24 nanometers, 65 nanometers, where low-cos doesn't work anymore and you have to use STI, shallow trench isolation. You will always have to compensate for the change in topology by using planarization. More specifically, chemical-mechanical planarization, also known simply as polishing, where you take the wafer with the oxide, with the bumps, and basically sandpaper away the bumps in order to avoid irreversible crystal damage on your silicon wafer, or with the metal interconnects, damage to the wires. You have to use a layer of protective silicon nitride, which serves as an end stop for the polisher, by making use of the fact that the selectivity from low temperature oxide to nitride is between 100 to 1 and 1000 to 1, depending on the density of that said oxide. The drawback from nitride is that it has a very high dielectric constant, which in turn increases the capacity between the metal layers. As you can see here in those pictures, on the left there is an implementation which skips the planarization step between the metal depositions. As you can see, anything more complicated than a single metal interconnect layer becomes unfeasible without polishing steps in between. On the right you see an implementation using planarization in between the interconnect steps, which gives us a really nice interconnect structure without hardly any connectivity issues. When performing a CMP step, the CMP end stop nitride layer must never be omitted. Failure to applying a nitride CMP end stop before depositing the oxide will lead to damaged structures. It's important to note that you also have to take into account etch effects on wafers. The planarization will never be 100% even, but more in a concave shape, because the force distribution from the center towards the edge goes down towards the edge. So you have to calculate enough thick nitride and enough oxide to have an even distribution with tolerance ranges, so that you can compensate for the edge effects. Those edge effects exist always, but the bigger the wafer, the more even the distribution. This means with bigger wafers, you have a higher yield, because the area in which you polish away the exact right amount is higher the bigger the wafer. This is the reason why in the industry there is a push towards bigger and bigger substrate wafers. The process itself is pretty simple. First you apply a pad oxide so that the nitride sticks. Then you apply the nitride, and on top of that you apply the isolation oxide. Then you polish it away. In order to have proper metal interconnect without any broken wires, I highly suggest following somehow along the lines of the process design I made for the HKUST laboratory. As you can see here, before etching the vias touching down to the transistor, I first deposited an adhesion layer for the nitride protective layer, the CMP stop, the so-called pad oxide, which makes sure that the nitride nicely adheres to all the different materials. Then I deposited plenty of oxide, in this case 1 micron, because it's a 1 micron feature size we have been producing. And then after polishing, depositing photoresist, exposing, developing and etching the contacts. Then in the next step, where the metal layer is deposited. In our case, we were using silicide thin film layers in order to reduce the sheet resistance of our transistor junctions. Because you cannot directly contact with aluminum onto silicide, because aluminum atoms would travel into the silicide and would increase the resistance of that silicide. I had to introduce a nickel diffusion barrier between the aluminum and the silicide. Adding a nickel finish between every aluminum layer has the nice side effect that the aluminum wires do not oxidize during handling. Since I already touched on how CMPing works, namely being some kind of sandpapering on a micro scale, I'll go a little bit more into detail here and explain to you with some example how CMP works and how it actually looks like in practice. So what you have is the wafer carrier holding a wafer towards the surface with some polishing pad. On this polishing pad you dispense a solution in which nanoparticles are being dissolved, like for instance ceria, industrial ceramic. Then you apply a well-defined pressure, which you set in the control panel of the CMP machine. Here on the right is a picture of a very affordable laboratory level CMP machine, which you can find online on Alibaba, for instance. There is no problem in case you want to start a startup and start manufacturing chips to just settle for this really affordable small one until you can afford an upgrade. Here a little example of a CMP machine and how it's being used. This is the unipole I showed you in the slides, and that's basically a demo video. As you can see, first of all, the mat is being fixed and now the slurry. The liquid with the industrial ceramic nanoparticles is being put onto this mat. Then a holder with the wafer samples downward is being put on and screwed in, and the rotation speed is being set in the interface. The rate can be calculated based on test wafers which have been fed through first and measured. Here is an entire wafer being polished with the special setup. Same thing, you span it in, set the rotation speed, set the pressure on the holder, and then you let it run. Silicon is called a semiconductor because it isn't really a good conductor, neither is it really a good isolator. Only when you dope it, it will start conducting well. You have the choice to either use more electrons, so elements which have a higher electron number in the shell than silicon, or you can use so-called holes by doping it with an element which has a lower electron number in the shell than silicon. This causes those before mentioned P and N junctions. You have actually three methods how you can introduce additional elements into a monocrystalline or polycrystalline silicon lattice, either through diffusion with a gas or with pre-deposition using liquid deposition with a spin coater, or you can use an ion implanter. Pre-deposition with a dopant gas is not so different to pre-depositing those dopants by dissolving them in a liquid and pre-depositing them on the wafer by using a spin coater. There is only a few additional steps which make it worth considering as an alternative to using boron gas, because boron gas is regulated and might pose problems during acquisition as a small startup which doesn't have all the licenses yet. For diffusion and pre-deposition with a liquid dopant, you typically use a tube furnace, like depicted here as a schematic, where you have a tube, typically made from quartz glass, highly temperature resistant, in a box. Inside the box you have heating elements which heat the quartz tube up from the center towards outside, which causes thermal zones. Typically in the middle of the box you have the desired temperature range you set in the configuration of the tube furnace. The silicon wafers are put into little glass boats, holders with slits in which you put the wafer in, like those old school CD-ROM holders. This quartz glass boat is made from the same material as the quartz tube in the furnace and can survive those very high temperatures. After positioning those wafers in the glass boat is then placed in the tube and shoved approximately into the center where the thermal zone with desired heat range is located. There are big versions of those tube furnaces. The industrial scale can be seen on the left here in the slides, while a small, low-cost laboratory variant can be seen on the right in those slides. Both, however, work the exact same way, just the scales differ. One thing to note about those furnaces is that you have the possibility to flush the tube with an inert gas like nitrogen in order to avoid reactions when not desired, which would happen if your material would be reacting in a high temperature with oxygen from the atmosphere. The before mentioned ion implantation is being performed with really ginormous particle accelerators, which could stem from some James Bond movie and thought of by some insane bond villain, but they are reality used in industrial setups. However, small startup foundries most likely cannot afford to buy such a machine, so I will not go further into detail. The main problem we have at Libresilicon is the chemical vapor deposition step, because most gases needed for recipes for things like polysilicon, which is required to form polysilicon gates, or for depositing the low temperature oxide, require silane gas SiH4, which is strictly regulated and has been used in World War II as a nerve agent. It might pose a real problem to get the licenses needed to acquire such gases. We here at Libresilicon work on developing alternative recipes which can achieve the same results: silicon nitride, polysilicon, and silicon oxide formation without the need for a highly poisonous and regulated gas. For depositing metals, which are required for the metal interconnects, or also for depositing metal which can be reacted in an RTP furnace in order to form silicide, a sputtering machine is probably the easiest solution. A sputterer in general is basically permamagnets, which in conjunction with a sputtering target, the desired material which is supposed to be deposited on the sample as a thin film, the material and the magnets together form a magnetron like the one you're used to from your microwave oven in your kitchen. In a low pressure atmosphere, the plasma ejected from the metal is traveling through the low pressure atmosphere to the substrate due to an electric field thanks to the power supply. Everyone who ever accidentally or by purpose has put a piece of metal into the microwave oven knows this effect. Those sparks, that's plasma. In those slides on the left you can see a typical industrial large sputterer, while on the right you can see a low-cost laboratory-friendly variant which is available on Alibaba and other Chinese supplier websites. Here you can see a plasma discharge from a self-made sputterer. Credits go to the channel Applied Science on YouTube. When it comes to etching the microstructure on your wafer, you have two options. Either you go the wet etching route, or you can spend a little bit more money and go the dry etching route with a plasma etcher. For wet etching, there is a few common recipes, chemicals used for certain materials. For instance, hydrofluoric acid for etching silicon oxide, metals, TMAH for etching silicon and polysilicon, KOH for the same purpose as TMAH, piranha solution, which is hydrogen peroxide and sulfuric acid and water. That is being used in case you want to perform silicide formation. That has delivered the best results in the laboratory to clean away unreacted metal after the silicide formation from the wafer. And H3PO4 for etching silicon nitride. The disadvantage of wet etching is that it is a highly isotropic etching, and while dry etching produces much better and sharper results. Also, with dry etching you have a better control over the depth and the etch rate. In general, when you etch, you have to keep in mind that the bigger the attack area of the acid, the higher the etch rate. This is the reason for design rules which define the size of a via in order to have a better control over and under etch. In this slide you see the difference. Isotropic etching on the left, which etches further horizontally as it etches down, So you will have an edge further than the mask. While with dry etching you have a nicely vertical edge down and virtually no horizontal etching. It is important to note that all the chemicals I listed before for wet etching are highly poisonous and super duper deadly when handled wrong. So, just to be sure and to make sure that you cannot sue me in case you die from handling those chemicals, I now tell you to wear a PPE. It's not a political statement, trust me. It's just really take precautions so that you don't get poisoned, okay? Also, little piece of advice, look at the poison data sheet of each of the chemicals and maybe dilute those chemicals to a degree where a single drop won't just kill you immediately. It's anyway better to have diluted etchants because the slower the etch rate, the better the depth control. In case you really don't know how to properly handle poisonous chemicals, ask someone who knows. Maybe not the obnoxious neighborhood Karen who wears a PPE when she's going to buy groceries. Ask someone who really knows what they're doing. But if you're unsure and you don't feel 100% confident handling those chemicals, please don't be ashamed to ask for advice. For wet etching, you can either go professional with a big wet station, like here on the slides on the left, or you can go like small scale laboratory, like with this little mini home wet station from Jerry Ellsworth uses in her video Cooking with Jerry, making microchips at home. Or you can actually also use Tupperware to have your chemicals in there. Just as mentioned before, make sure that it's sufficiently diluted. Don't put food into containers where you stored poisonous chemicals. Keep that stuff separated. Don't drink it. Don't put it into your eyes. Common sense. Dry etching, also known as plasma etching, can be described as sort of an inverse sputtering because it's a similar principle. In a low pressure atmosphere, etching gas chemical mix is being flushed into the low pressure chamber and then agitated by an RF setup which bombards the target and removes the atoms from the target atom by atom. So that's a schematic of the thing. You have coils which agitate the gas and turn it into a plasma, which then bombards the sample you want to etch, and all the areas which are not protected by a photoresist layer are being removed atom by atom. Here is an example. On the left, you see an industrial scale dry etching machine as it's being used in factories. On the right, you see a low-cost laboratory variant. As mentioned, in order to etch those structures, we of course need to first somehow transfer those images we designed in our layout tools onto the wafer. For that purpose, we use something called photolithography. In its principle, the same as developing a photograph. You have a photoactive resist, which is being deposited onto a wafer using spin coating. And after that, you use UV light, which you focus and beam through a mask of some sort on which your pattern is being painted on. Then this pattern is being focused again and being projected onto the photoresist, which chemically reacts in the areas where UV light hits the resist. And after development, your structures have been transferred onto the wafer. Typically in industrial setups, you use something like a big stepper unit, which takes cassettes full of wafers. As mentioned in the beginning, batch loads those wafers. and the patterns are being laser printed onto a glass plate which is coated with a metal of some sort. On the right you see a mask with 4 of the layers for our Libresilicon test wafer. This is one of the masks from the mask set we used in HKUST to test Libresilicon with their equipment. The stepper aligner then takes those patterns from those masks and scales them down in size and repeatedly exposes the same pattern onto the wafer, one next to each other. The result is this tile pattern you see on this wafer. This is the repeated same pattern exposed over and over again by the stepper. The result you can see here, that's transistors we did for the Libresilicon project. Those are special transistor test structures to characterize our process. And on the very right you see those little specks on the wafer, that's dust. The problem with mask lithography is that mask making is very expensive. So for a laboratory setup, it makes sense to have a maskless stepper aligner, which uses a DMD display, that's a micro mirror device. It's the same type of technology used in projectors for home cinema. As a matter of fact, Sam Seeloff did build his own maskless stepper aligner, hooking up a projector to a microscope. We at Libresilicon are right now working on a maskless stepper aligner design inspired by Sam Seeloff's design, just that our design will be more integrated and with parts which can be reordered easily. Here you can see a spin coater in action. Credits go to Holography Homel. I assume they mean Holography Home Lab. It's spelled the way like here in the white text, Holography Homel, in case you want to go check them out. The specs in our test structures, which I mentioned in the last slides, can be really impactful when your microstructures shrink in size. Here you have an overview about different types of of particles floating through the air at any given time in a non-clean room environment. For instance, a skin scale, the thing your body loses all the time, is around 10 microns. Same goes for a hair, the diameter even a little bit more than 10 microns. Pieces of insects floating around, let's say 100 microns. Yeah. Then we have here starch. Here the scale 1 micron, so that thing is also around 100 microns in diameter. Wood particle, 100 microns. Pollen, 50 micron. Then fungal spores, 30 microns. You get the idea. You have to get that stuff out of the air you're working with your microstructures. If you have 10 millimeters transistors or so, it's not a big problem. 50 microns, you already cannot get anything working out of your manufacturing attempts if you have mold in your garage. So you have to make sure that the air is somewhat clean. The smaller the structures, the more impactful particles floating in the air. So you should really think about some contamination control measures in the area you are working. Because if you have like a 1 micron node, you try to make 1 micron transistors or even 500 nanometers, and you have like 10 micron particles. That's basically like an asteroid crashing into your integrated circuits. So if you really want to go high tech, submicron, 500 nanometers or less, you should really wear proper cleanroom garment in a cleanroom environment, wear latex gloves and surgical mask. And again, that's not a political statement, but if you don't do that, your circuits will just not work. Upside, due to the current crisis, surgical masks and gloves are super inexpensive at the moment. A box with cleanroom with gloves, huh? Gloves, awesome. A whole box, I think 100 gloves, huh? For like 10 euros. Reduced price. Really awesome. So I have enough gloves to work with chips. Also surgical masks, super cheap. Now we only have to gaslight people into thinking that they can slow the spread by wearing bunny suits, because those are still super expensive. When it comes to cleanroom environments, you either can go hardcore professional with a big cleanroom with laminar flow all through the room in a bunny suit. Those people, by the way, what are they doing wrong? They're not wearing masks. Again, not a political statement, just a point about contamination control. You see, the light here is yellow. Yellow light is typically used for photolithography areas in a laboratory because the photoresists are made in a fashion that are not reactive to yellow light. In a clean room, you typically have two circulatory systems. One system pumps the air which is already in the room through multiple stages of HEPA filters, pumps it back through the ceiling, blowing all the dust towards the floor, where the air is either sucked in sideways or in some instances through perforated floorboards in the bottom of the room. Then you have a second pump system which pumps fresh air in, filtrates this air through multiple filters from the biggest particles, and then the HEPA grades increase until you have fresh air, so that you don't suffocate in the clean room, which has been filtrated to the clean room level degree required for the work environment. There is also the possibility to refurbish used shipping containers in case you do not want to build a factory building, or you can have your cleanroom environment in a glove box form factor, where you don't even have to wear a cleanroom suit and other protective gear, because between you and your samples is the gloves of the glove box. The conclusion from those explanations is that you certainly will need a furnace for the CVD and diffusion steps. You will need a sputter in order to deposit metal for the interconnects. You need a wet station to clean your wafer in between the steps. You need a PPE so that you don't accidentally poison yourself, or at least reduce the risk that you accidentally poison yourself. You need a lithography system of some kind to transfer the patterns from your computer to your wafer. You need a microscope to check whether the structures turned out the way they're supposed to. And you need some way to keep the gigantic particles away from your microstructures. Good to have in case you want to do anything more complicated than 1 micron structures with one single metal interconnect layer would be a CMP machine. And if you want to go submicron, you totally need a dry etcher. Optionally, in case you want to do something like annealing titanium on top of silicon in order to produce titanium silicide in order to reduce the sheet resistance of your transistors. You will need a rapid thermal processing furnace. And if you have some bitcoins left on your wallet, you can also buy an ion implanter. Now that I've been talking so much about the manufacturing side of things, let me tell you that Libresilicon is not only how to manufacture the actual physical chips, but we also work on the software side and design tool side. So the Libresilicon PDK contains, among other things, the design rules, which are a direct result of the limitations of the machines and other process parameters. We also provide a collection of cores which you can use in your layouts, like analog digital converters and digital analog converters, flash cells, and RAM. Also basic components like resistors, diodes, guide how to build inductors. If you have the possibility to use iron in the process, you can also build inductors. And then we have the EDA tools. You can either use QFlow, which includes Magic, Grey Wolf, QRouter, and Yosis, or you can use OpenLane, which is a concurrent project, but we cooperate with them. Under pdklibresilicon.com, you can have a test run of our standard cell generator, which generates standard logic cells based on design rules you provide to that tool. The tool itself, of course, is Libresilicon, is open source and can be downloaded from GitHub. Our team has public weekly mumble sessions every Sunday, 1800 Zulu, so 6 p.m. UTC, on murmurlibresilicon.com. We also have a mailing list, and if you're really in dire straits, you can drop me a direct email to my email address here. Because I'm not a friend of getting government funding, because I'm not a fan of using money which has been extorted by the government from honest, hardworking people in form of taxes, I would appreciate donations on this dedicated Bitcoin wallet for this talk. I would have a much better feeling if I knew that the money I'm using for this project has been given voluntarily to me. Thanks for watching.